Okay, hi. I will begin the webinar about the generalized stochastic dual dynamic programming and its relation with real-time distributed optimization. Okay, this is the index of the presentation. I continue. Okay, in the beginning, I will speak about the mathematical and informatic revolution to give you the idea why the vendors that the theory of vendors that I will present today is very important. I think that the first mathematical revolution was the algebra. The algebraic language, the algebraic notation is general, is a standard to write about the mathematical models in this moment. And we have many optimization and modeling technology that use algebra as his basic language. We speak about algebraic computer language. I think that the difference between the algebra in the college and the algebra in the profession is that we need to learn about to write very good algebraic models in order to represent the real life world. The second revolution, I think that was the classical optimization was the central of the end of this revolution was Lagrange theory, that is the base of all the formal mathematical model for optimization, okay? The third revolution may be the revolution due to the digital computers that begin in the past century at the end of the Second World War. Okay, and the main people is Dasik and Kantorovich, and we begin here to think about the new type of mathematicals, the mathematical oriented to computers. And the last revolution, I think that is the parallel optimization, is the parallel parallel models, the thing that we have big problems and we can divide the problems in order to solve very large problems. And this revolution begins in the 1960 of the past century. Okay, we can synthesize the relation in this part that is all the large-scale optimization methodologies that use mathematical formulation, algebraic formulation, we can assume that the first or the main relation is that two different problems can speak between them. And the key is the duality theory, because one problem sent information about the dual variables and the another problem sent information about primal variables. And this is the formal base of this is the duality theory. Okay, then at the end of this revolution, we have the different levels of to make big models. The first level is the basic solvers, like Simplex, like Gurobi. Then the basic solver is oriented to solve a format, a mathematical problem that has a special format, maybe linear programming, mixed linear programming, quadratic programming, nonlinear programming. Okay, the second level is the large-scale technologies, okay? And we have many large-scale technologies that all use the basic solvers. And at the end, in the third level, we can speak about the integrate all this information using the concept of cross-decomposition, okay, that was developed by Van Roy, the main basis, okay, and we can solve now problems using concept of parallel optimization, asynchronous parallel optimization, and we can send all of these unique related with stochastic programming that in this moment is the best of the optimization technologies, and that we can use stochastic programming to solve real problem very big in this moment. Okay. If we see the speed of the solution of the problem is the combination of three aspects. First, the computer technology. Second, the basic algorithms like Gurobi, Simplex, or another. And third, the use of large-scale methodologies. Okay, we have many types of processor in this moment, and we have that these processors are related with these different types of algorithms. Here we can have, for example, GPUs that are more oriented to matricial operations, and at the top we have a CPU that is more oriented to large-scale methodologies. Okay, but we can combine it, all this informatic power, to solve very real problem, very large problem. Now we have a new revolution in the informatics, that is the quantum computers. When the quantum computer, we need to change the form that we think about the how is the structure of the computation. Okay, we change from the bit to the qubit. From this, in the beginning we use 0-1 representation, and in this moment the net representation is 0 between 0 and 1 is the real the idea about qubits. I don't understand this very well, but the more important part of this is the speed off of the technologies. Okay, we can. This is the expected growing of the speed of the calculus. Then we can solve very large problems in this moment, because we have a big power, informative computer power, to solve this type of problems. 20 years ago, it started different reports GAMS about the sequential, when we compare sequential or integrate form of solution a problem. In this moment, for any problem, for some problem, we need 15 hours, but with parallel only 200 CPUs. This is the relation. See, 15 minutes to 50 hours. And the precision is different. Now we are in 2020. This is, the relation is more bigger. Then we need to solve in the future, to solve problems, we need to understand that the speed of the computers are very high, that we need to think in another dimension, in another way, because the sequential calculus is part of the past of the mathematical. Now we need to think and to understand the parallel mathematics and his implication to solve very large problems. Okay, then this is the intro. I introduced these ideas. I choose Bender's theory because I think that Bender's is the main theory that we need to understand the parallel computation in this moment, and we can use these ideas to try to two problems talk between them, and we can use all these ideas in the future. I think for me, vendors is as transcendental like Danzig, is my idea. Okay, this is the history, the resume of vendors. He died some years ago, in 2015, he died. And this is the history about the use of vendor theory. Okay, this is a report was 5 years ago. Okay, I think that in this moment we have a real, okay, we have a real growing of the use of vendor, and this is related, and this is due to the relation with the parallel computers that we can use today, because many years ago, okay, the problem was the cost of the parallel computing. In this moment, $100, we can rent a computer with that have many CPUs. Then it's easy to implement this type of methodologies. We don't need millions of dollars to work in this. Then the people discover vendors. Okay, and this is my history working with the vendors. And in this part, I begin to work with vendors many years ago, 40 years ago, when we try to solve real problems in computers that that have 1 megabyte of RAM memory. It's very difficult to put the model in the memory of the computer. Then we need to decompose the model using large-scale methodologies to put the model in the computer. And another part was to try to solve the model. Okay. Then in this moment, for real problems, the idea of vendors was real because this was the only way to try to solve problems, real problems. And in this moment, I work in design electricity distribution networks, in water resource operations, multi-reservoirs system operation, okay? And I begin to work, and in this moment, I am part of this growing. I work all my professional life. I has using vendor beginning in this moment, okay? 40 years ago, 45 years ago at least. Okay, why vendors and why large-scale methodology? Because we have two alternatives to solve a problem. We can solve a problem, try to use sequential or the ideas about sequential calculation, and then we generate a problem oriented to use a solver and solve the problem with the solver, working with an integrate model. But if you use large-scale technologies like vendors, we can divide the problem in many sub-problems, and this is the speed of the relation between the standard oriented integrate models and the models oriented to use vendors or to use large-scale technologies. It's important that vendor is one of the large-scale technologies. The another important is Lagrangian relaxation and dancing wall decomposition. But in this conference, we are interested in to study, understand and study vendors. Okay, and the relation then, this is the relation for the mean of the problems that these people report, okay? And the relation when the complexity of the model grows, okay, we have more complexity, the relation is begin to be, it will be exponential. Okay, this is the real. Then many people think that the metaheuristic are better to solve a problem, a real complex problem, and that the mathematical programming or exact models. But in general, these people compare his solutions or their solution with the integrated approach, not with the best approach, okay? And we have many studies that make that vendors is growing in the speed of the solution of the problem. Then we will work in this conference. We will be speak about the vendors, and I present very rapidly the theory. During the conference, I don't try to explain the mathematical relation. I can give you all the support, mathematical support to understand the technologies. The more important part is to try to understand the concepts. Okay, the basic concepts, how vendors is the base to build a new form to view the mathematical modeling. Okay, then I am writing a book, and I can give you in the final version of this PDF that I put in the web. I have many chapters in this book about vendors and about the topics that I will be trying to explain the concept during this conference. Then I am trying to explain the basic vendors theory. Okay, vendors divide the problem in two types of variables. Okay, and the word that they use vendors is partitioning. Okay, they divide the problem in two types of variables, the complex variables and the simple variables, and they use, okay, then my original optimization problem has a linear model over the simple variable, the x, and a complex model for the I variables, okay, that may be discrete or may be nonlinear. Then they put the part about they take the subproblem about the simple variables. That is a linear problem. This is important for the conference. And this is the form of this part of the problem. Okay, we have two parts of the problem, y that are related with this problem that is a subproblem related with x variables. Now we change the representation of this subproblem. Okay, this is the primal version. Now we can use the dual version. Okay. But that for linear models has a very important advantage that the dual problem is independent of x. Then we can put this directly in this problem, see, that is only in terms of y. Then the vendors, we can understand that we have, this is the feasible region of the dual problem. We can represent the feasible region about the extreme points of the polyhedron, okay? And if we have finite points, we can replace this feasible region for these Cutting planes. It's the same problem. The real problems is that for the real life problem, okay, the number of Cutting planes that we need are infinite, okay, because this is a very big feasible region with infinite or non-numerable string points. Then we need a mechanism, okay, to generate these cutting planes, and this is vendors, okay. They establish a conversation between the two subproblems, the subproblem in the simple variable that must be linear for vendor basic, and the problem for the coordinator that may be linear, mixed linear, non-linear, mixed inter and non-linear problem, okay? And we establish here a conversation. The coordinator sent to the subproblem primary variables, and the subproblem sent to the coordinator dual variables. Okay. We are trying to represent this. This is the feasible zone of Y, and when we generate cutting planes, see, we cut the feasible region, okay, trying to get to reduce the feasible region only to the region that is related with the optimal point, see, of Y and X. And but here we can have problems, because it's possible that when we send primary variables, these problems don't have solution. Then here we have an unfeasible solution, okay? If we have an unfeasible solution, the dual problem has, see, unlimited, unbounded solution, okay? And then we have two types, or another type of scoot, vendor scoot, that is related with the feasible zone. Then vendors generate the standard vendor, the basic vendors, generate two types of spotting planes. One, try to get the optimality, okay? The discard part, this scoot, the discard values of G because they cannot be optimal. And this another cutting plane, okay, discard values of G because they don't permit feasible values of X. And this is vendors, okay. We have is a dual, is a primal model, because vendors work in the feasible and estimate using duality theory, the gap, and at the end, see, in a finite number of iteration, we solve the problem. Vendors develop these ideas to solve a mixed integer problem, linear problem with integer variables. Okay, this is the way that we can see the loop between the different problems. But the most important is that we have two problems speaking, because we speak the coordinator and speak the subproblem. And another part that is very important is that for the large scale methodologies is that it's possible that within the large scale methodology, like mathematical tricks to solve the problem. But in the reality, the large scale methodologies has an techno-economic interpretation, and we need to understand that we are dividing not the problem, the mathematical problem, we're dividing the world in relation between the parts of the world that are related with the parts of the mathematical problem that represent the real world. Okay, for example, here we have the optimal function. Okay, what's happened? We can, for linear problems, this part is represented. We can represent this optimal function by hyperplanes, okay? And vendors begin how? He send first one hyperplane, okay? The second hyperplane, the second cutting plane, third cutting plane, and at the end he represents the real function by a set of hyperplanes, okay? But they only, vendors only use the hyperplanes that are related with the zone where is located the optimal solution of the problem, okay? Because the number of these hyperplanes may be non-numerable, may be infinite, okay? This is important. Okay, the main limitation of vendors is that the subproblem must be linear. And the reality in the world is that the problems in the world are non-linear and are discrete, mixed. The real way, for me, in my understanding, the real world is mixed, is non-linear system. Okay, then we have variation about vendors. I don't speak in this webinar, this variation, but the first variation, important variation, is call it the generalized vendor decomposition that was developed by Arthur Geoffrion 50 years ago, and they permit that the nonlinear subproblems. And another variation that is very important is the variation about the discrete subproblems. That when we have mixed integer variables, see, binary or integer variables in the subproblems. There are many works in this area, in this way, but the real, one of the main important research is oriented to use the concept of Gomory codes to solve integer problems. Okay, then we change the variation, change the model because they have 3 problems, okay? They have the coordinator, they have the Bendis standard subproblem, and they have a Gomory codes subproblem, and we can establish a different conversation between the subproblems, but it's possible to solve the problem, making variation in the basic theory. Okay, but the basic theory is for linear programming. Okay, this is the first part. Now we can go into vendors to use vendor for another cases different than the basic model. Okay, this is the basic model. Okay, we have coordination variables. Okay, and we have a linear model. We can see this linear model as an integrate model, but in the real world, this matrix ever has special structures. And one of the special structures is when this structure is a diagonal block diagonal matrix. We call this type of structure dual angular matrix. Okay, and then we can use this, we can use vendors to divide the problem. Okay, we divide the problem in the variables y and the x. We have n blocks here. Then we generate many problems. The main aspect of this characteristic of this diagonal is that the problems are in the problems on x sub I or sub n are independent. Okay? Then when we see this part, we don't have an integrate problem. We have n and we don't have an integrated problem. We have n independent problem that we can solve parallel. Because then we can develop it, we can use vendor, and we can develop the theory of the composition, vendor's theory. We can, in order to generate another type of cutting planes, okay? We have the original problem. We apply the standard vendors, and we generate. We generate here a standard coordination. We call this couplet. Okay, but we may see about the more deep the structures and the relation between when we make the composition. And we have many three cases basically. The standard vendors, good, when we see the subproblem as an integrate problem, okay, then we solve in one iteration the subproblem, and we generate dual variables, and we insert here one cutting plane. And we continue to generate another value of the primal variables, y, and continue. But we can make a different, we can see a different point of view, and we can see the subproblem as independent subproblems that we can solve parallel, and where each subproblem sends his own variable, dual variables, and we can include in the coordinators, see, multiple vendors codes, and we call it the couplet vendors code. Okay, with the couplet vendors, okay, we have more deep codes because each subproblem are sending the information. And we have another, and we can, if we continue to study the characteristics of the problem, we can, a special case that I call unified vendors codes. That is when I can use only one subproblem, and this may be any of all the subproblem in the second level, in the level of subproblems. Okay, we have 3 subproblems, for example, but we can choose any of the 3, and all of the subproblems may generate codes for all subproblems. Okay, this is very important because in this case we only use one subproblem to generate multiple codes, and this may be independent of the number of subproblems that we have. Then if we have here, we have infinite subproblems, okay? We can, with only one, generate infinite cutting planes. It's more, we can generate cutting planes, but for the cases that I know, but I can generate codes by the cases that I don't know about the case. And this may be in a sample process in stochastic optimization, in which we are making the sampling during the optimization, okay? Then we have 3 types, and this is important because we need to study, and we can take advantage of this type of possibilities. These are the result is this, that all this effort, the result is that we need less time to solve the problem. This is the relation, see, reported 2 years ago, 3 years ago, see, about the relation between one single code and the couplet use multiple codes, okay? The people interested in this, I have a paper, white paper, in which I speak, show all the theory. From the point of view of the computer, okay, then we can, when we divide make the decomposition, okay, we must assign the processor, see, to different types of subproblems, to the coordination subproblems and to the subproblems. The subproblem may be related with periods, see, time, with region, sector, function, or with random X scenarios when we are speaking about stochastic optimization. And we can, if we may some we study more the cases, we can make a mixing of point of view of the same problem. And this topic I don't speak in this webinar, but it's possible. And all is oriented to speed up the solution time. Okay. Basis of these ideas, one of the main important works is the L-shaped method of bandit-like and wets. That was oriented to stochastic optimization, two-stage stochastic optimization. The L-shaped method is a case of the composition they solve, and they show how can we use these ideas to solve the problem, to solve the two-stage stochastic optimization. And this work was in 50 years ago. Okay. Okay, we speak about the decomposition, but we have another case that is multi-level vendors theory. Multi-level vendors theory, you can read another white paper. Okay, I will put in the last version of this PDF all the reference. Okay, about the multi-level vendors decomposition theory. What happened? It's possible that we can see this. Okay, we begin with the G. Why this variable? This was the coordinator variables and the coordinated variables. See here, but we have more than one level. Okay, then we can establish this is the problem. We can apply vendor, the original vendors, to solve the problems. And then this is we begin to divide the problem and to apply vendors. This is the presentation, but we go to the end. That is here. Okay. Then in the first step, we make the first partition. Okay, we divide. Okay, this is the upper level of the system. Okay, that is based in the variables y, and in the second we have the variable theta, and in the third we have the variable x. Okay, then we can make this type of partition, see, that we call it multi-level vendors theory. Okay, the limitation for the original case is here, this is the general coordinator. It may be this any format, linear programming, mixed, non-linear, but these problems beginning for the second level all must be linear. We can relate this with time, because, and this is important because at the end of this the conference, we are oriented to speak about dynamic systems, about time. Okay, but we can apply the same and see. And this is the first period, the second period, and the end, the last period. Okay, and when we developed many years ago the general theory for a triangular matrix, because it's possible that we have relation at the end of in the last period, this is the period S, okay, may be related with variables in the first period. Okay, this is a general view of a dynamic system. It is possible. Okay. And this is then we have a theory, basic theory for decomposition. We have a basic theory for multi-level vendors partitioning. I use this, and we implemented this in 30 years ago to solve real problems in mini computers. All this theory was the first step to solve the problem. Then now I will speak about the dynamics aspect of the problems, okay? Because one of the point of view to modeling is the dynamic, and we can use the concept of dynamic programming to introduce the dynamic modeling, and the person that introduced the ideas about dynamic programming was Professor Bellman. This is the general structure about dynamic programming. We have many periods, period 1 until period last period, see, and we have two types of variables. This is the more important, and this may be very important in the theory, in the general theory that we have. First, we have control variables. See, we have state variables. These are the two variables of the system. The state variable represents the state of the system, normally related with the stocks. This is one of the representations that is standard. We have stocks, inventories. Okay, the inventory is part of the state variables. But we have another variables that are the control variables. The main characteristic of these variables is his effect is only the same period of the at which is associated the control variables. Okay, we have another part. We have the call function or the return function. Okay, and we have a transformation in the stage, in the period, during the period, okay, that and then we can express how is the state variable at the end of the period if we know the state of the variable at the beginning of the period and we know the control variables. Then this is the standard problem that formulate Professor Bellman, okay. It's important that all this has a real life representation. For example, here the state variable may be stock, storage, capacity, state of the matchings on off, okay? And normally the control variables are related with the activity levels of the equipment, okay? And we have a representation for many systems, okay. It's important that what I think Bellman saying that if I know how work the system from if I have first stage of first period, second period, third period that go to the end, is I know how is the best way to go to the period previous to the last. See, if I know these values, okay, then we can optimize the best decision in this stage. Now, with this defined, we can include this here, and I can solve the problem then for this for the previous period, and we can apply the same idea. Okay, and solve the problem. The accumulation of these values of the function or the cost function is the future cost of the system. And when we solve the problem, if we have all this information and I solve the problem for the first period, I can solve all the problem. Then we have the optimality principle of Bellman, see? In which he defined an optimal path, see, had the property of the fact that anyone that it will be initial decision and the state, the remaining decision should constitute an optimal path with respect to the resultant stage of the first decision. This is the central idea of Bellman. Okay, this is an example of the problem for linear dynamic programming. The origin of the dynamic programming is important because dynamic programming was oriented to solve the problem numerically, not using the formulation as mathematical programming, because maybe very difficult, mainly when we try to solve a stochastic programming. Okay, it's important that the dynamic programming grows oriented to solve a stochastic dynamic programming is the real many forms of the try to solve the problem. Okay, and the form to solve the problem is I begin with the last period, I build the future cost. Okay, this is a very simple problem because it's the last. Then I solve the problem between the previous t-1, t upper, -1, and t, and we must include in, and this is the backward phase. Okay, when we arrive to the first period, we know the solution. Now we need to rebuild the solution, and this is the second phase, the forward. But in the beginning, dynamic programming solved the problem using numerical optimization, tables, and more oriented with to stochastic programming. This is reality, and mainly in the electrical sector. And then when we have many stable variables, this was impossible to solve. And if we see here, when we have problems related with electricity, with water resources, the state variables are related with the reservoirs, with the stock of water in the reservoirs. This is the state variables. And then the table that was very difficult to management. Then the people call the curse of dimensionality problem. Then that implies that the dynamic programming can solve very problems with very little amount of reservoirs. This is the reality. Then it was a problem, okay? And then the next step was to try to use the vendors, and some people work and make the link between the vendors theory and dynamic programming and the problem that has trying to solve very large problem using the concept of dynamic programming. This is the origin, for me, in my interpretation, of one method that is called dual dynamic programming. And it's important because dual dynamic programming is very, the people in the electric sector knows very good about the dual dynamic programming as his stochastic version is the DDP, stochastic dual dynamic programming. But dual dynamic programming is part of one of type of models that is more general models that is called nested vendor decomposition. Okay, there are DDP, dual dynamic programming, is one of the types of models that we can build using the concept of vendors to make dynamic decomposition. Okay, which is the difference? Which is the idea? And the main problem and the main limitation about DDP for now. This is the structure of dynamic programming. We have control variables, we have state variables. Okay, these are the two types of variables that we have. But the people who works, and there are many algorithms that may be classified as nested vendor decomposition, like DDP, okay, only see the problem converting all the control variables in state variables. Okay, they eliminate the concept of control variables. They only use state variables. Then this model is bigger in the matrix, is integrate, okay, and they develop all the theory. It's a good theory. The theory is convergent. But here we can see how we can apply vendor decomposition. This is the real problem of dynamic programming, but only considering only state variables. Okay, then we can divide the problem in two, because vendor divide the problem, partition the problem into parts, coordinator and subproblem. This is the basic vendors. And all the algorithms that may be called nested vendors use the concept of vendors. Then we divide the problem in coordinator and subproblem, or we can the problem in coordinator and subproblem. We have two different, but it's the same. At the end, it's the same. Here we can divide the problem again. Okay, we divide the problem coordinator and subproblem, and then we need to divide the subproblem, see, in coordinator and subproblem until the last stage, so the last period. Yeah, if we use this approach, it's the same. The solution is the same problem. Then we need to divide the coordinator, see, the coordinator in one subproblem, one coordinator and another subproblem, and we can to build all the steps to solve the problem. The main problem here is this implied that this subproblem must be linear. Must be linear, okay? Then the only stage that may be nonlinear, discrete or nonlinear, may be the first coordinator for the first period. The rest of if you use standard vendors, okay, all the problem must be linear and must be continuous. They use the concept of future cost function, like dynamic programming. This is one of the ideas because why I call dynamic programming, okay? And there are there are more than many formulations. All are the same in the end. Okay, the more in the electric sector, the more know is the formulation that's developed Pereira and Pinto in beginning in this paper, I think. We developed with another group of research, another similar but different in the notation and formulation of dual dynamic programming. As I say, the multi-level vendors theory, okay, is equivalent to nested vendors. But we see it's only question of how I am accustomed to see the presentation. Years ago, I worked in the nonlinear dual dynamic programming, in which I was convergent. It was during my doctoral thesis working to include in the model the subproblem, nonlinear subproblem, because the reality that we need is convenient to have nonlinear subproblem. Then This is the basic idea about nested vendors. The next step is stochastic nested vendors that are similar, in which stochastic dual dynamic programming is one of the methodologies. Here we have when we see the how can solution the problem to include stochastic scenarios in the problem, we need to, it's important that we can begin to think in many ways to solve the problem. And these ways are heuristics ways, because it's not true that there exists the correct way, okay? Then we need to see how, okay, if we remember, we have here, when we make this step, backward and forward, we have now, when we have a deterministic model, there are only one way to make this, okay? Strictly. When we have a stochastic model, we have many scenarios, we have many relations, and we build many forms to make, to solve, because it's possible when we are solving, for example, this problem, okay, the problems that are in the middle, that are coordinators and are subproblems, can generate information for the previous stage and for the posterior stage. And then, okay, what can I do? I can continue to the previous stage, or I can go to this posterior stage, or if I am solving the problem in a parallel way, how can I do? There are many ways, and I think that this part is art. It's not science, but here we need to understand how in the moment the way to make this process, the backward and forward process. Then and we call this the sampling methods, okay? Entonces there are at least, you can understand, you can read about this, but fast forward, fast backward, fast forward, fast backward, dynamic, fast forward, fast backward. So, and all are different in the way, in the approach to the sampling. That implying the approach, how can solve the different problems. At the end, all are convergent, see, but the speed is different. Here we have 6 type of problems. We have different sampling methods, and we have difference. See, some very large, another may be short. Okay, this is maybe the best. Okay, the dynamic, fast forward, fast backward. Okay, then there are many algorithms. See, for many researchers, that one of them is stochastic dual dynamic programming. The another is abridged nested vendors. There are many. There are a chapter in my book about this, trying to make a resume. Okay, in the electric sector, the SDDP is the more used. Okay, this is the abridged, and we can see here. This is a report of Donoghue and Belch about the relation between the two methods, and it's important that for this case, in this report, okay, the sampling approach generate very big difference between two algorithms that in the basic are the same algorithm, because the two algorithms are nested vendors, the composition algorithms. But the difference is very important, okay? But we need to make clarity about the how can compare different algorithms to try to establish which is the best way to solve a problem. And here we have, this is a report by GAMS. GAMS is a General Algebraic Modeling System, a company, the name of a company that produces GAMS. The people, the mathematical model, the majority that work in optimization know about GAMS. GAMS begin in 1885, in the past century, okay? And here they reported two types. The world is reported by GAMS, okay? They implement SDDP in GAMS, and they implement SDDP in C. It's different technology. This is C++ using concept technology of iLog, okay? And this is the SDDP using computer language GAMS. And these are three options of GAMS, four options of GAMS. And this is the relation. The relation is 1 to 35 times. That means that the benchmark in a no-controlled environment may be distorted, okay? It's very important because I don't know, I don't remember in this moment, but the only way to make the good comparison is if all the elements are compared. But if we take the report of SDDP and I implement my version of A and B, okay, it's possible that the difference may be between due to the form of the implementation, because we have this difference, okay, between the same technology and between different technology. It's important when we speak about this. But the reality is that the large-scale technologies speed up the solution. Okay, there are many works that extended the variation. We can call variation about the SDDP and about the another's methodology. But the more known is SDDP, in my opinion. Okay, here we begin my work. This work began in the first version of this approach was implemented. I am not an academic people. I am a consulting and a researcher. Then I don't the first publication about this generalized dual dynamic programming was 20 years ago, but the first implementation was 30 years ago. Okay, because we begin to work with this idea to solve general problem, to try to solve very big problems in personal computers. Okay, there are a chapter about all the theory. I try to explain the ideas. This is the DDP, the dual dynamic programming. Why I put generalized? Because I see it's only, I choose this, the DDP, because maybe generalized nested vendors. Two, by generalized, that is the difference between this vision is in the control variables. Okay, the control variables are different, are included explicitly, see, are included directly in the model GDDP, but the control variables are not included directly in the GDDP. This is the main difference, and they difference make a very big difference. Okay. This is the formal. We can have there are an equivalent. I have this is the same problem, but the modeling is different. Okay, when we have this representation, the characteristics of the representation is the same characteristics that the dynamic programming. Basically, we can see what's happening. More or less, we divide this approach. We divide the problem in two types of variables: the state variables and the control variables. Okay, there are two types of variables different. Okay, we then this is a more specific matrix. Okay, we have a representation, general representation of the problem. And now we will apply vendors. Then we partition the problem in state variables and control variables, and we can solve it using two approaches for the coordinator. We can use an integrate vendors coordinator, or we can use a dual dynamic programming coordinator. Okay? We have these two alternatives. Okay, the real idea is that we have in a real, the state variables only affect the process, okay, which are the type of state variables are the levels of activity of the industrial infrastructure, of the industrial equipments, okay? And the coordination, the state variables are assignment of resources and stocks, and this is the relation. Okay, really, first we can apply two types of vendors. We can two steps to apply vendors. The first is that we make the difference between state variables and control variables, and we generate a problem. This is the subproblem that we have for each period. Okay, this is for each period. It's a function for this function. Okay, when we see, okay, we can apply vendors and to solve the problem, but we have an interpretation. It is related with the Cobb-Douglas production functions. In real, we are producing here, see, the productivity function of these levels. And in economics, that the people in economics try to model in aggregate way the system, okay, in economics, when the people and the professional use Cobb-Douglas functions to represent the functioning, see, of a sector, for example. Okay, they have resources here, they have capital and technology, or maybe capital workforce, and Q is the production, and this is a Cobb-Douglas function. The problem is in vendor is that this type of schools represent the Cobb-Douglas function. The unified vendor schools or the vendor schools, see, represent the Cobb-Douglas function. Then we can solve the problem in this way. Okay? If we solve the problem in this way, we have only one coordinator, and only here we have these two problems, and we use this must be linear, and here this may be linear, non-linear, mixed. Okay. This is the one way. The another way is to, okay, we can apply this problem has only state variables because because we made the partition between state variables and control variables. Then this problem only have state variables, and if we remember, dual dynamic programming and nested vendors decomposition are oriented to solve problems that only have state variables. Then here we can apply the theory of dual dynamic programming. Okay, then we can make this structure. This is the structure in which we have a system, okay? And we apply in the coordinator dual dynamic programming, and we have for each period a subproblem related with the state, with the control variables to solve the problem. The main problem is that if we use this approach, this problem must be linear. If we try to use another type of model, we can apply vendors directly. In this case, we can apply for any type of problem. We can apply vendors. This is an important difference. Okay. Then this is the general structure. We can see that we can associate this with the codes, the vendors code. We have two types of vendor codes. The vendors code that generates these subproblems, and the vendors code that generate these subproblems, and the vendors code that generate the subproblems in the coordinator. Okay, these codes, they are related with the code, the future cost function, and these costs are related with the Cobb-Douglas production functions. This is the representation. Then, in any case, we can use, depending on the structure of the problem, we can use decoupled codes or unified codes. If we can use unified codes, we have here a very big advantage. Okay, then it's important that we can try to have this part, or to drive this part, to have unified codes that may be very important to the speed up of the solution. Okay, here, this is the resume of the DDP of the nested vendors, compared with generalized dual dynamic programming, and the result, the conclusion is more robust because can solve more type of problems. Okay, the implementation, the people who are interested in see the implementation, this is explained in a paper. The result that we have two implementations, one in our technology tool that we call Optex, and directly the implementation that we make to produce all the results that I am presenting. That it was developed in GAMS and managed directly by the modelers. Okay. Then this is the implementation. There are two implementations. The implementation following the by the coordinator in using DDP, using an integrate coordinator. We have here assigned the process, the problems to different processors. Okay? And the logic may be explained in another opportunity, or maybe read in the papers. Okay. The application in the sector electric. There are a paper that resumed this with more detail. This was all was solved in GAM, so we used the best option that was SolveLink. This is the computer in which run the cases. It's a personal computer. And we take a reference to make all the problems for the electric sector using the case of the IEEE association. Okay, and if we see this is the problem. 12 hydro plants, 8 reservoirs, 6 thermal plants, 1 deficit plant, the deficit, and we simulate by hours. This was the idea, the general idea. Okay, this is the case. It's possible to see the case. This is the structure. It's important, this system is similar, maybe bigger than a system than a country, a little country like Panama, for example. Okay, with the 12 hydro plants, big hydro plant may be higher. There are other countries that have many hydro plants. Okay, but this was the selected. These are the formulation. Then we make some dispatch model. This is the first type of examples. We consider one linear model to, digamos, standard economic dispatch, in which all was considered linear. The idea is to, this is the formulation. This is the formulation of this model as a program, dynamic programming. These are the state variables, okay? And these are the control variables. In this case, the control variables are very simple because we are not including in this experiment any type of transmission network. So only all the equipments, all the generators are in the same bus, only one bus. Okay. Then we have the formulation of the GDP coordinator and the GDP subproblem. In words, the coordinator is the hydropower system coordinator. Coordinator is oriented to coordinate the use of the reservoirs, and the subproblem are oriented to the thermopower system. If we have a transmission, the transmission must be in the subsystem. Okay, then we for this case we use the standard for many cases. The unified vendors goods, only one period generating goods for all periods. It may be applied. Okay, it's possible. Then we can decide and to prove which order. Okay, if we only need to solve one problem to generate goods for all problems, in this case, we only need to solve one of these subproblems. We have 24 subproblems for 24 hours in a day. We for unified. We can solve only one. When we are working with the coupling codes, we generate the 24 codes, but we need to solve 24 problems. In this case, we generate only, we solve only one problem, and it generates codes for all problems. And with this approach, we go to the coordinator and we generate a new set of variables to continue optimization. The results are okay. These are three types of orders. Try to see the impact of the order in the solution. Then we begin with the first. See, then the second in each iteration, and key ordinate, we make alternate orders. This is what the order, and this we ordinate the progress by an indicator that was, for instance, in this case, the energy demand. These are, we make some experiments. One is the integrated model, another was the solving the dispatch, the linear dispatch using unified codes. The other was solve the dispatch using the couplet codes. See, okay. Here we solve all the problems. Here we solve only one problem and generate 24 codes. Another was the DDP, to compare to the DDP. And another coordinator, we have two alternatives to the couplet codes with integrate coordinator to the couplet codes with DDP coordinator. Here we have the solutions. I go to the final issues. Okay. Here we can see some. Basically, the problem is very little, and the best way ever was the full, because for little problems, it don't make sense to use very large, very power tools like large scale optimization. Then it's more the overhead. But when we go, we can compare between them. Okay, this is the idea. And in this case, we think that this is important, the order. It's important to say that we have 24 problems, and was not necessary to solve the 24 problems at least one time. The algorithm generate the codes, the appropriate codes for, in some cases, for five or six sub-problems that never was solved. Well, not necessary, because the information was enough to that we don't need to solve them in never. The couplet, because this is the case, was not, is best the unified when it's possible to use. Okay, the DDP, we have difference, and the standard and the coordinators, the DDP, the integrate was better. But it's important that the complexity of the problem is very low. Then it is a conclusion that must be revised. Here we have all the solutions. Then we make another examples with a mixed linear model, type unit commitment model, in which we have a start plant, the thermal plant. We can stop start. Okay, in each period we must decide we continue operation or we begin the operation. Then we have a mixed linear model. In this case, we can use the DDP. We can the new variables, the start variables are part of the state variables. It's a standard that if you have a start-stop modeling, it must be similar, is oriented with the state of the equipment. If the state is on/off, and the more convenient is to model in the coordinator. This is the representation. Then our coordinator has two parts: the start-stop thermal plant and the hydropower. And here we have the thermopower system. And here we have the solution. At the beginning, the model is very simple, and the best way is the full space. At the end, if we divide for a day, for example, and here we begin with the 24 periods, and this is a period for 15 minutes, okay, for the day, if I don't. Okay, this is very young. The detail is when we go by this level, see the number of periods, it's imposed, the full space can solve the problem. Can solve the problem in 1,000 seconds. Okay, and this continues to solving the problem. The GDDP continues to solving the problem. Then we can conclude, the conclusions are very simple, okay? EDPP approach is faster than DDP and can solve very large, we can include this more and more power cases, more complex cases. The next part is the theory of GDDP. It's very, there are another papers that we describe this part. We only include the ones, we include scenarios, okay, scenarios in the demand, mainly, I think. We associate the probability of the scenario, okay, and the modeling was using non-anticipative constraint. This is a standard I prefer for all models of stochastic programming. We have here a deterministic model, see, and we include anticipative constraints. This is the way. Then this is the scenario, the anticipative constraint, which we can permit to model this type of scenarios without problem. We split the variables, we aggregate the variable by nodes, and we include anticipative values, forcing that, for example, here this and this and this must be equal, yeah, and these are the type of anticipative constraints. Here, okay, we can vary two types of approach to solve the problem. One is to have only one coordinator for the process and for the random scenarios, and another is to have the anticipative constraints as a coordinator, maybe a Lagrangian coordinator, and divide the problems in two. We use, in this case, we use only one coordinator. See? Then we have the scenario 1 has 3 periods in this case, and 3 periods is scenario H, and we have subproblems, and it's similar. We only have 2 index in each subproblem, the index of periods and the index of the scenario, random scenario. Again, we can use for the structure of the problem, we can use unified Bender-Scots. And this was the problem that we solved. We can in this case, we can use, is the same, we can use for the coordinator, we can use, we can decompose the coordinator using nested benders, and we decompose each period in state and control variables. And we can use unified vendors if the structure of the matrix are appropriate. Okay, and they have a relation. This is the implementation. Okay, the implementation, that was the implementation for the multi-case with unified vendors costs. This is the flow chart. And it's important to, in the case of stochastic modeling, when we have two types of convergence, one is the equivalent deterministic. We generate an equivalent, a deterministic equivalent to the stochastic model, and the another is the stochastic convergence, in which we don't have, we do during the optimization process, we generate scenarios. Okay, the two approach may be useful depending on which is the case that we are working. Okay, what happened with this? Suppose that we have many scenarios, and the reality is that we can begin with a little scenarios, for example, with two random, two conditions, and we can check and introduce more scenarios, more random scenarios that represent more random problems, random period problems during the optimization. It's important that when we have unified vendor codes, because the vendor codes that I generate when only using one or two, and maybe I may begin with only one scenario. We generate codes. When we introduce more scenarios, more periods, or more random scenarios, the codes that I generate may be used by this. And we can, the first step to include more scenarios is to include the vendor code that are valid for this, that are valid for this, and this speed off the time of the solution. At the end, we generate all the information that I need, but it's possible to only consider the, for example, for the statistical stochastic convergence or statistical convergence, then the costs that it's possible that the process stop here and never know that the information about these two scenarios because was not necessary. Okay, but when we include new scenarios, the story of the code is useful for all cases. That is very important because the speed of is very high. Okay, these are represented the cases, yeah, the stochastic model. The first was oriented to compare a nested vendor approach like SDDP with the GDP. Okay, we can conclude that for these cases, this was the relation. Okay, it's important that we develop the two versions. Then suppose that we don't have it's controlled the environment. Okay. If we for mid coordinator, okay, and this is for linear model. For linear coordinator, there are cases that integrate, don't have can't solve the problem because the problem is memory. It's important that if we don't divide the model, okay, the first reason that oriented me to use vendor not was the speed of the solution of the problem, because we don't have experience in this moment to solution the problem, was oriented to manage the problem in the memory, because we have a real problem and we have only 1 megabyte of memory. then it's impossible to try to put a real in the problem with the expanded matrix or with compressed matrix techniques in the memory if we have a stochastic model and we have a good amount of scenarios. This is the relation we can here we use until then we begin to increment the number of scenarios. And this was the number of scenarios controlled. This is the number of variables, 2 million variables. 6 million of constraints. This is the integrated model, the equivalent, in 10 millions of variables. Okay. When we compare the time per scenario, the time spent, the time solution per scenario, we have this is the component, the comportment. See, this is the history. At the beginning was high, the time per scenario. See, time per scenario was high, okay. And they go and he's established. Okay, this is very important because this is the comportment. This is typical when we have a process or an algorithm that is learning. Because at the beginning we don't have information and we spend time to learning about the system. And when we learn about the system, we don't need to learn more, and we have enough information, and this is the level of knowledge that we have about the system. Okay? And this is try standard. The standard is that this time is exponential. Here, this time try to be linear. And this is the case for unified codes. That means that is related with the learning process, implied that we don't have study. Here we have it is necessary for the people. It's necessary to have to know that it's important to have many scenarios when we need to have very good approximation to the real world, because when we have a little amount of scenario, the approximation is very bad. This is a strategy was taken from a Professor James Murphy paper. Okay, we solved the problem with statistical convergence without problem. Then we go to a mixed nonlinear problem. For this case, we alterate the network, and we suppose that we can reuse the water by the pumping station that put the water in the upper part of this chain, network chain, water network. Okay. And this pumping station is not linear. Okay, then we must include, this is the modeling of the pumping. This is the modeling of the pumping. And for this case and for the algorithm, we prefer to put the pumping in the coordinator. Okay, in the coordinator, we put the pumping, and we solve the problems. These are the history. It's important. These cases is not possible to solve with the theory of nested vendors because he can drive nonlinear models or mixed nonlinear models. Another proof was include risk management in the modeling. Okay, then for this case we assume the problem of expansion in order to study the risks associated with investors with the investment. This was the possibilities, okay, for expansion in the hydro plants, 2 expansion in reservoir, 3 expansion in thermal plants, okay. This is the demand, okay. We change the demand, and the demand maybe was changed to grow. And these are we include in the model the formulation of Rockefeller for conditional value at risk, okay, that try to control the risk in the conditional. This is the value of the conditional value at risk. This is the value at risk. This is the distribution of cost, of the distribution of revenue, and we control this variable. This is the variable that we control. This is the formulation. The formulation is easy, and this is then we try. The idea is that we try to control this empiric distribution. See? We try to reduce the cost in order to reduce the risk. It implies that we pay a price for reduce the risk. She assume more and more costs in the medium, okay? And mainly this is possible that we reduce in the minimum cost we must to pay in order to control this. These are the solution. And we work with the very good amount of scenarios, okay? And this is the time spent. Here we have the same component, okay? He go, and in this case more difficult, and then it's more difficult to establish the cost here in this part. But we see studies of how work the human body. This is the standard form of formulation, and we have this type of learning at the beginning. Therefore, is bigger. Then we can conclude that this work. Okay, this is the conclusion. Then we go to the end to think about the future which is the state and work in this. We can make a mix, okay, between multi-level and decomposition vendors theory, okay? Then we define 2 words: partition, the action of dividing the problem in 2 subproblems, establishing a hierarchic relationship between them. Decomposition, the action of divide the problem in multiple subproblems with the same level in a hierarchic scale. I mean, system, multi-sector system that is this. We can go to this. Suppose that we have this model. This is an integrated model, the investments, and operations. Okay? We can make the first partition. We divide the model in investment, that is a mixed coordinator, normally 0, 1 binary variables, and operation, that is the integrated operation model. But the reality is that we have many sectors. For example, the energy sector, and we have one sector and other sectors, X sector, and we have 3 levels of system. We can apply again vendors, and we can divide the problem by zones. We have 4 levels, and now we can divide in periods, okay? And we have the time at the end. That is the real atom of the system, because this system, the functioning of this system is the sum of what's happening in each of these subproblems, okay? This is the real work. These problems are very, very little, because it's 1 per period, and very similar, because maybe in one period, the system may be similar to another period. And this, we can apply GDDP is oriented to this, that multi-level vendors is oriented to the rest to coordinate all the system. See? But now we can integrate the models of random condition, stochastic programming. Okay, then we divide the problems in two stochastic, in two or more stochastic conditions, H in this case. And in this case, again, we make all the partitions, we have at the end a time atom, and this is the structure of a of the general stochastic dual dynamic programming. Then we can make many things if we have developed and we can generate the problems. We can see the system as a series of family problems, see, related between them. All the conversation between them, this is the represent the coordinator of investment, the vice president of finance, for example. This is the coordinator. This is a logical coordinator, but it may be at this level we have the coordinator of all operation, and here we have the old sector, and we have the sector one coordinator or by sectors. Then we can see our problem as a set of problems that have a conversation between them, in which we have an optimization database that may be in memory or maybe in disk, in RAM, in disk, no problem, in which we have different types of problems in which all put the information in variables, primal variables, and dual variables. And we need to define a protocol to communication. We don't see here this this level, that the problem establish a conversation with this. Not this problem and this and this and this broadcast his results in a database, and all the problem go to the optimization database and take the information and produce the solution. Okay, this structure is similar to the artificial neural nets. When we think, the difference is that in the artificial neural net, the conventional, we have a structure that his mathematical relation are empirics, are try to perceive the reality, in which we can change this structure by a mathematical programming. Okay? Then we can name to use to represent the each part. This is the structure of an hypothalamus of the human beings. Okay, then we have functions, see, and we have memory, and we have connections, and all work together in this using this idea. And then we can call this an hypothalamus. And this is one of the ideas. All that we make using parallel computation, parallel mathematics may be used for decompose the real world. Okay, we can see the large-scale optimization problem like a mathematical algorithm that solves a problem. But the reality is that we have a real world in which we have functions and levels of hierarchy between them. And we can, if we go to large-scale technology, we divide the problem. See, in this case, for example, central government and sectorial. The sectorial are represented by the Cobb-Douglas reduction, and all this is the real representation of the system when we try to make an organizational and technical and economic interpretation. okay? But it's important that if we see the system as a whole, see, it's impossible to see the relation between the parts. This is a wall. This is a big rock. But when we divide the system and we see the conversation, that the conversation is primal variables and dual variables, we can understand what has happened between the agents that are working together. Okay, it's impossible if we don't see the world as separate parts because are different. Then we can begin that, and this is a real case that we developed for a petroleum company in which we develop 4 models, see, one for production, one for multi-mode transport products, one for refining, one for pipe transport model, okay? And we use all the models, see, can work together, see, and independently putting in a offline database the results, or in real time putting the results in a real-time database in memory, for example. And we can coordinate this using large-scale methodologies. And into each model, we can use again large-scale methodologies. Then we can see in the future that we need to divide the process, see, in the oriented to make large-scale system using asynchronous parallel optimization to produce artificial enterprise hypothalamus. This is maybe. Finally, we can see what is the future. And for example, in the electric sector, we can see the problem of the financial transmission rights. The difference between the traditional optimization is that the optimization traditionally we see only the dispatch, but the actual power technologies permits to co-optimize transmission topology, distribution topology, generation dispatch simultaneously. Because today it's possible to change this during the operation. Then this is the problem of financial transmission rights. This is the case in the PGM zone in the northeast in the States. They need to solve problems every 5 minutes, okay? They means that this is the amount of money involved, see, that they can think that they can avoid or they can reduce, see, and it is good for the people because low cost for the energy, okay? And we need to solve this with complex model. This is a model reported in this paper. Yeah, we have the paper. But if we try and use the concept of GDP and multi-level vendor decomposition, we can see that this system we have for each period, 5 period minutes, see, we need to solve the problem. We have the problem, have 2 parts, the generation part and the transmission part, okay? The generation consuming part and the transmission network, okay? We can see this all of only one problem. It's very difficult to solve in the time that they need. And we can see this as the different 2 levels between the 2 problems. One is the transmission network and another the generation. Then we can include this here using vendor codes. But if we think the transmission network maybe change, but we can model that we don't change, and we can use only unified approach, unified vendor codes, in order that we solution a little amount of problems, and we generate codes for all sub-problems, and we can solve the problem in very short time. Finally, all this idea was implemented in our technology that is Optex. Optex is a way to see that we don't are not interested into develop programs using programs. We have a robot. The robot was beginning here, write the programs. He write the programs. Then in the last decade of the past century, we begin to develop Optex, and we begin with generic multi-level and dynamic vendors to solve problems in PCs. Actually, we generate programs in GAM, sample, or PL using the concept of GDDP, formally, that I tell. We are developing our language, okay? More simple than the language like GAMS or like AMPL, because it bases in another idea. As a robot, he generates all the interface, because the solutions, one part of the solution is the database. Then it's necessary to generate the structures and to permit to the modeler to access the databases. He generates programs in real in a language, in a computer language. He generates a large-scale optimization program. Then, okay, we don't need to write the programs, the GDDP programs. Okay, we need to configure how is the programs. Okay, and he generates. Then he helps us to produce hypothalamus, artificial hypothalamus. How are included in Optex the large scale optimization? We are developing. We develop, and we are developing, because it's continual research, a control panel, like a standard solver, okay? Because what happened with the research about the large-scale technologies, I am speaking about vendors, Lagrangian, cross decomposition. We have many options. The researchers have produced many knowledge in different forms that we don't have integrated in a machine that can understand all the results of these researchers. Then we can. Then that means that a user can select as a parameter of the generator of the program, which is the type of optimization that of the algorithm that he needs. Okay, and we are developing systems. We have two systems: the energy, electricity, and gas system, and the smart grid optimization models, all integrated around a big database in real. Then these are models all can talk between them, okay, very easy. And our models can use generalized stochastic dual dynamic programming, not only for the competitive dispatch that is the standard, no. Any type. If I have a problem of maintenance optimization, it's a dynamic problem, similar that has involved stochastic optimization, then I only need to say that I need. This is the form that we define a problem. We here define two problems. The problem mod benco, that is the coordinator problem, and the problem mod ben nunum. This is the code. These are these two problems. We define the restrictions the constraints that are associated with this problem, and we define the role, which is the coordinator and which is the subproblem. Here we have a model. The model is the integration of two problems, problem 1 and problem 2, and he produced the problem, the problem to solve the real case, only from the formulation of the deterministic model and some other parameters. It's included that we have the vendor's codes. We see that the models run forever, not for one time. Okay, it's possible to use tomorrow the results of the codes to begin to warm start, see, in the tomorrow. Then it's included that in the optimization process, the codes, that means in this case maybe the Cobb-Douglas functions or that are the vendor's code as they use it. This is the presentation. Thank you for your attention. And if you have questions, please, I try to solve them. You can use your microphone if you like. Some question? Okay. If you don't have question, I thank you for your attention, for your time. I put the version in the URL, the LinkedIn link. I put the last version of this with all the links to the technical papers. And we are open and interested in to work with the people that are interested in this type of research. Thank you. Have a good time.